this is supposed to be a rather simple lecture, while the second lecture for today is much more complicated, much more technical. The subject is Thouless-Anderson-Palmer equations, which is a substitute for the case of spin glasses for usual Ginzburg-Landau equations for a second-order phase transition. Let me write it down. Standard Ginzburg-Landau functional for the order parameter phi. We know that phase transition happens at the point where the coefficient in front of phi squared is 0. And it is negative below Tc. So when this function free energy as function of the order parameter acquires such a form, which means that a trivial solution with 0 order parameter is unstable. And instead we should find another solution here, which describes the ordered phase. Now, the subject of this paper of Thouless, Anderson, and Palmer, which I'm going to explain you, is how to write down a similar in major idea, the similar equation for the case of spin glasses. In spin glasses, as I explained in the previous lecture, you don't have a simple order parameter, because what you have is some thermal average on each side where spin is sitting. There is some non-zero thermal average. But on the other hand, if you average bar overline means average of the system, this average is 0. So, which makes a problem to introduce some standard order parameter of the kind of Ginzburg-Landau theory. So how to do, what to do with this problem? This is what was resolved in this famous paper. For the case of a spin glass model with all-to-all interaction, Sherrington-Kirkpatrick model of a spin glass, Hamiltonian you see here, and J, Ij are random numbers with Gaussian distribution. And these matrix elements J, Ij do not depend on a distance between spins. So there is no real Euclidean distance in this model. There is an equal probability to find some value of jij for any pairs. It is extremely simplified model, but still rather non-trivial. Here, you see two different numbers, z and n. Z is a number of neighbors of each spin, and n is a total number of spin. But in Sherrington-Kirkpatrick model, z is equal to n. So always everybody is coupled. Good. Let's try to follow the derivation which was presented in this paper. First of all, let us consider high temperature expansion for the partition function. The exponent of beta is inverse temperature, of course. The exponent of beta Js Isj can be written exactly as shown in this equation 3. And then let us calculate free energy. So to calculate free energy, you need to take a logarithm of this trace and then average it over disorder. The next line, second line of this equation, tells you that there is a trivial average of logarithm of product of this cosine beta j, and then non-trivial part with the second term with logarithm of trace of this product for various pairs I and j. Here Tij is hyperbolic tangents beta jij. This is formal expansion. Now the angular brackets means averaging over distribution of j. Since this distribution is a Gaussian function with zero average, in order to have non-zero terms, we need to take all pairs or all links ij twice. Otherwise, it would be zero. So this is why these three rules here are formulated. Then you can express this expansion of free energy in terms of such a loop diagram.